initial mass, 54,000 tons. It contained 50,000 tons of fuel. That's to go to Proxima Centauri. One way. By the way, most of this interstellar stuff right now is a one-way trip, so just be ready. Okay? You're not coming home. Okay, for a variety of reasons, it turns out. But anyway, as I said, 50,000 tons of fuel, 54,000 tons for the spacecraft, 500 tons of payload. Okay. And this craft could reach 12% the speed of light. Now, the other thing I wanted, you see, this is the Saturn V by comparison to Delius. Okay? By comparison, it contained 5.6 million pounds of fuel compared to 50,000 tons. Okay, and it would take also like 42 years, 50 years to get to the nearest star. Okay. Now, one thing that's interesting too is the density of the fuel. A grain of fuel, deuterium tritium, the size of a grain of sand, can produce as much energy as a gallon of conventional rocket fuel. Okay? And so it's very, very good for interstellar space travel. It would take between 30 and 90 days to get to Mars. And of the 30 days, 3 days would be spent accelerating to the speed to go to Mars, and 3 days to slow down. Now, big problem, fuel. Remember, 500,000 tons of fuel for this craft. What if your craft, and what we really need is lighter spacecraft, cheaper fuel, less fuel. Well, something was proposed, something called the Bussard ram scoop. Okay, the Bussard ram scoop says, don't carry 500,000 tons of fuel. You carry less, and you pick it. Oops, excuse me, and you pick up the rest from outer space. Okay, hey, it sounds like a good idea, right? So you have the scoop, and it gathers up interstellar space. Interstellar space contains hydrogen and helium. Fortunately, it doesn't contain very much. It actually contains 10 to the minus 21 kilograms of mass per cubic meter of space. So you have to scan about a volume equivalent to the planet Earth to get one cubic meter of hydrogen. All right, so 10 to the 21 cubic meters of space, volume, and you collect your energy. But anyway, the collectors on the starships are here. They're called a NECEL. Okay, but anyway, so Star Trek actually used this. Mr. Bussard was an American physicist. I believe he graduated from Princeton, and he worked primarily in the area of fusion reactions. Okay, it's going to take a long time. Okay, so what we might do is create a spaceship that's so big, called a generation ship. And for example, at 1/10 the speed of light, if we wanted to go to Kepler 186f that we talked about earlier, it would take 5,000 years to get there. Okay, so many generations would go by, and so they're talking about creating spaceships this big. Obviously, you're never going to launch those off the Earth, right? Anyway, I thought I'd show you that. You get a little chuckle, but who knows? Remember, keep an open mind. Now, the way that seems to be more practical, if we could get there, is antimatter. Okay, antimatter propulsion results in an effective velocity of 69% the speed of light. Okay, and 462.3 million miles per hour, or 70% the speed of light, could take you to Alpha Centauri in about 6 years. Okay, this is one technique for, antimatter propulsion. Okay, where you take a piece of matter and a piece of antimatter. Antimatter, I don't know if I said already, but that's where instead of negative electrons, you have positive positrons, and instead of protons, you have a negative equivalent of antimatter. The thing that's interesting about antimatter is there's very little of it. In fact, there should have been the same amount of matter as antimatter in the Big Bang, but for some reason, which we still don't know, all the antimatter has sort of been very hard. It's just very little. So we got to make it, or we got to harvest it. I mean, if we make it, it costs $100 trillion per gram. If we harvest it, it may cost about $10 billion per gram. Well, that sounds like a little, but 1/10,000th of a gram of antimatter is all you need to go to Jupiter. Okay? So that's on the good side. And also, it's very good for interstellar space travel in that it would only need 100 tons of antimatter to get to the nearest star. Of course, you have to be able to contain 100 tons of antimatter. And if you don't, you could literally blow up the world. Literally. Many times over, I would think. Okay. Antimatter is 1 billion times more powerful than conventional fuel, 1,000 times more powerful than nuclear fission, and 300 times more powerful than fusion. So you got the power there, the bang's there. Right now, and when you bring the matter and antimatter together, you create energy and something called pions, as well as an extensive amount of gamma rays. In fact, so many gamma rays that your rocket may become radioactive. Okay, so shielding becomes a very important issue. Okay, now what you see here, this is one. You bring them together, you use a magnetic nozzle to convert the orbital motion of your pions to thrust, and that's what you have here. This one's a little different. You remember the pulse nuclear fission rockets? Well, now we're talking about using antimatter to cause fission explosions and have a sail called, and this thing is called a Medusa sail, and use sail-powered spacecraft with explosions of nuclear bombs to power your spacecraft. So that's antimatter. Main thing now, cost. The only way we have to make antimatter is with the Large Hadron Collider in Switzerland. Okay, and that only costs $100 trillion per gram. Okay, but another way that we could use is it turns out that cosmic rays from the sun interacting with the atmosphere actually produces antimatter also. Not a large quantity, and it could be harvested, which we don't know how to do yet, but it will be possible. Okay, finally. Okay, faster than light travel. Sorry, not there today, but maybe. Okay, and we'll talk a little bit about faster than light travel. All the technologies I showed you earlier did not get you to the speed of light. Well, the speed of light, it turns out, is really impossible to get to, quote unquote, because according to Einstein's special theory of relativity, as you approach the speed of light, mass increases to infinity. And so you can't push your craft that fast. That's one problem. Another problem, which can be good or bad depending on how you look at it, is time dilation. 1 hour of spacecraft time traveling at 99% the speed of light is equivalent to 1 year of time on Earth. I've seen a head shake. You got some other number to give me?
There is no such thing as bogus math.
Well, okay, well, all I'm saying is that's the theory, the stuff that's there.
The hypotenuse of a right triangle differs
Well,
through if time is slower.
okay, well.
Your timepiece is slower, but not time itself.
Your timepiece is slower, but your measure, well, we can talk about this later. Okay, anyway. This time dilation is proven to be a fact, even if the math is that your GPS would not work today if you don't account for time dilation. Okay? In fact, the clock on board the spacecraft would go 1/7 millionth of a second slower than your clock on Earth. Okay? These numbers I know are facts, so it'd be interesting to talk to you later. But anyway, so that's the issue there with time. So traveling faster than light is not practical. However, you can travel faster than light if you take advantage of a quirk in the theory of relativity. Specifically, you can warp space. A scientist, Miguel Alcubierre, came up with a set of equations which suggest that time could be warped. And he came up with this warping technique where this is this little ball here. You create a wave, okay, a lot like a walkway at an airport, where you expand space-time behind the craft and compress it in front of the craft. Okay, and the act of doing this is creating a wave with that moves you forward without any time change in the spacecraft itself. So the spacecraft's time would be the same as the spacecraft on Earth. Within its bubble, the warp bubble, time is not speeding up. It's the same as the time that Earth has. Okay? Now, this is very good, except it needs exotic matter. Exotic matter is not antimatter. It has negative mass, and it causes things to fall up instead of down. Okay? So, we haven't yet found it. Well, we think we have some ideas. There's something called the Casimir effect, okay, which takes advantage of a quantum vacuum that develops between two pieces conducting metal plates brought to 1 atom distance from each other. It turns out that a vacuum is not a vacuum. Quantum particles constantly appear and vanish. Okay, and if you bring the plates close enough together, then we are excluding certain quantum particles that are bigger than the distance between those two plates. As a result, you create something called a quantum vacuum. That quantum vacuum is representative of exotic matter. Okay? Now, the problem with this technique was that this little band over here, it was originally the width of a wedding ring. As such, it would have required a glob of exotic matter the size of Jupiter to power it. Okay? However, Harold White from NASA modified this little craft by increasing the thickness of the ring, okay, which is the ring of negative energy, okay, and oscillating the ring. The result has been that he's reduced the amount of exotic matter to the size of the Viking spacecraft. A lot more practical. Okay, the amount of exotic matter we've found so far is almost nothing. Okay, so think positive, guys. Okay. So Mikio Kaku dubbed the Alcubierre notion as the passport to the universe. I mean, this is really the way to go if we can do it. And nothing says that that space-time can't go faster than light. It does. Remember I told you, the universe is expanding at 30 million billion times the speed of light. Hey, no, don't shake your head.
Can't stop me shaking my head.
That's all right, you can shake your head. I'll let you shake your head. But anyway, okay, so that's one technique. The next technique, of course, oops, I went the wrong way. Oops, I'm going the wrong way now. Let's see. Okay, wormholes and stargates. Okay, a wormhole first proposed by Albert Einstein and his friend Nathan Rosen, okay, called the Einstein-Rosen bridge. You see that over here. Links two places in space. Remember that I told you about that warp? You take space, you warp it, and then you have a tunnel between the two ends, so you go through the tunnel. Okay, this would allow you to get to any point in space or time. Okay, these two things don't have to be just space. It could actually be a time machine, going forward or back in time. They believe that when the universe was created, millions of little black holes were created. Okay, and these little black holes, they believe, may be associated with white holes at the other end. So whereas black holes pull everything in, white holes spit everything out. The problem with this technology, and by the way, this is being researched by James Woodward, and the other one is actually being researched by Harold White of NASA. I mean, and he's coming up with ideas. Remember, if you think negative, you're never going to go no place. Okay, put it bluntly. But you have to have an open mind. I believe, and it will happen. Okay, so anyway, this is the other technique for going faster than the speed of light. The problem with this technology is over here, you need another big glob of, guess what? Exotic matter. All right? How much? About the size of Jupiter, possibly a neutron star worked. Okay? We still haven't figured that out, and we haven't found a black hole that we could actually go into and test out these things. However, people are actually trying to create mini black holes, and they're actually looking at using the Large Hadron Collider to do that. So, is this really all science fiction? No, it's not. There are people actually looking at it, and DARPA thinks enough of it to give this group, the 100-year Starship group, $500,000 to actually look at the technology and see if they can come up with an actual working Starship within 100 years. I wish they would do it. I would be very happy. Fortunately, even 100 years, I'm not going to be here to see it. These groups are working on it with the 100-year Starship group. Project SETI, you may have heard of that. And then the British Interplanetary Society with its Project Icarus. Now, some technologies that are in use today, or being, I would say, proposed today. Okay, this is one, and I've been hearing a lot of negative about it, so don't hold your breath on this one. But this one is propulsion with no fuel at all. Okay, instead, it's like a giant like a microwave oven that produces what's the EM drive, okay, and it produces thrust by bombarding a plate and generating thrust. This, according to a lot of people, violates the third law of thermodynamics, and so may be a hoax. But NASA is actually researching it. And what we're showing you here is the difference in fuel. Remember, chemical rockets 10 to the 137 kilograms, more than the mass of the universe, and antimatter 100 tons. So we're moving in the right direction. This one excites me. The Skunk Works from Lockheed Martin, my company that I worked for a number of years. They've come up with a new proposal for and actually building a prototype. Okay, a fusion reactor about the size of a jet engine. And by the way, if you have companies, they're looking for partners, okay, on this one. And if this is real, that's a big step in the right direction. Because remember what I said about fusion power. Okay, so in conclusion, according to Carl Sagan, all civilizations must become spacefaring or extinct. And what we've seen so far are but baby steps in preparation for interstellar space travel. We still have a long way to go. A lot of it still looks like science fiction, but on the other hand, it's steps that we must take if we are to survive as a species. Which will it be when it comes to the whole of humanity? Who will help to turn the stream of interstellar space travel into reality? At the very least, let us pursue interstellar space travel for the same reasons older people, like us, me, plan